Okay, so we move on to the last unit of this CMOS VLSI, in which we'll try to see the dynamic logic circuits. Okay, so when I say dynamic logic circuits, you'll come to know what exactly these dynamic logic circuits are all about. And before that, we'll try to see one of the concept called voltage bootstrapping. Okay, so what is this voltage bootstrapping? We'll try to see now. So we are into the last unit, as I said, which is basically dynamic logic circuits, in which we have the first one, which we have voltage bootstrapping. Okay, so we'll see what exactly this voltage bootstrapping is all about. Okay, then after this, we will see the domino logic circuits, which is a part of dynamic logic circuit. And then we'll move on to the memory section. Okay, so in which we'll try to see the ROM, then the ESRAM, then the DRAM. So ESRAM basically stands for the static random access memory, whereas the DRAM stands for the dynamic random access memory. Okay, so this is what the agenda of the fourth unit is all about. Okay, so initially, so we'll start the final unit with what is called as the voltage bootstrapping. Okay, anyone heard about this terminology, voltage bootstrapping? Even it is applicable in your BJT also, but in this year it is, we'll see in the CMOS circuit what exactly this, not the CMOS exactly, so we'll try to see in the MOSFET. Okay, anyone knows what is this voltage bootstrapping is all about? Yes or no? Quickly. Okay, so I'll take an example. Before we go to the voltage bootstrapping, what exactly, we'll take an example of a MOS circuit. Okay, where I have two NMOS transistors named M1 and M2. So for M1 gate, I'm applying the input, the source is grounded. Between the M2 and M1, I'm taking what is called as V out. Okay, and the gate of M2, I'm naming it as something like Vx. Okay, and now this is a simple inverter kind of thing. So okay, and this is a simple inverter for me. Okay, and Vx, in order for M2 to be on, Vx can't be 0. Okay, so that's why we'll try to keep Vx to be something like VDD. Okay, in other words, we ensure that M2 is always on. So this is acting as a load kind of thing. Okay, so Vx is kept with VDD and Vin is the only variable. So now we'll try to see what is our V out. Okay, with respect to the load capacitance. This is CL. So when Vn is equal to 1, what happens to transistor M1? Fast. Anyone should reply fast. When Vn is equal to 1, that is logic high. What happens to my M1?
On.
It is on. Okay. When it is on, what will be my V out? That is voltage across capacitor. Fast. Yeah, what will be my V out? Okay, what is M2? Before I Go and check what is V out now. What is my M2? Whether it is on or off. Where Vx is VDD, it's on. Okay. So M2 is always on because Vx is VDD. Okay. And now I have given Vin to be logic 1, which is nothing but what VDD. Okay. That is 5 volts or 3 volts, whatever, depending upon the technology. M1 is on. What is my V out? Yes. What will be my V out when Vin is equal to 1 for this particular circuit that I have drawn? Fast. Yeah. It is 0, right? 0 volts. Yes. The moment when I change Vin from logic 1 to logic 0, that is 0 volts, what happens to my M1? It becomes off because the gate voltage is 0 for NMOS. The moment the gate voltage for NMOS is 0 means it is off. Now, who will tell me what is V out? Just a minute, I'll just give me a minute, I'll come back. Yeah, so now can anyone tell me what is V out now? When Vin is equal to 0, M1 is off, M2 is still on, gate voltage is at, this is gate, voltage is at VDD. What will be the V out now? Fast. Fast. What will be? It is VDD minus VTN. That is, I will take it as something like VT2 because it is the threshold voltage of this. So because now this M2 is simply acting as what? My M2 is simply acting as what now? Yes. Yes, what is my M2 is acting as when Vn is equal to 0?
Passive device.
Huh? Yes. Yes, Arjun, was it?
Yes, sir.
Yeah. What is my M2 is acting as? Just
Passive device.
passive device. No, passive it is a load. I know. But see, this M1 is not there. It is simply like this, right? This is VDD. This is VDD. And this is my V out. Okay. This looks something like what now? Or if you want to write, I'll write it in terms of this. Yes, gate is at VDD. Okay. Drain is at VDD. The source, which is nothing but what V out for me now. Tell me, what is this now? This is basically acting as what? NMOS transistor. Who will tell me? What is this acting as? Fast.
Pass transistor.
It is simply a pass transistor now, right? And we had seen in a pass transistor, okay, NMOS cannot conduct good one, it conducts bad one. So that's why you are getting V out to be something like VDD minus of threshold. Hope this is fine now. Yes. Now, when I want to switch this particular inverter, this is simply an inverter now. Yes. If I want to switch between 0 to 1, okay, I mean, I'm not getting the exact one at the output, that is the VDD, it is VDD minus VTS. So that means there is a drop in the threshold voltage at the output. Yes or no? Fast. Yes, no. Yes or no?
Yes, sir.
Yeah, so we had already seen what is a pass transistor. Gate is at VDD, okay. If drain is at VDD, okay. The source is nothing but what? I want to know, just I have to ensure that VGS is greater than the threshold. Okay, so VGS is nothing but what? VG minus VS. VG is at what? VDD. Yes. Suppose if I keep my source is also at VDD, my VGS difference is 0. 0 cannot be greater than VTH. This is what we had studied. Yes. Or the minimum VGS to be is VTH. So then source cannot reach VDD if drain is at VDD and gate is at VDD. The source maximum it can reach only VDD minus VTH. This is just a recap of the past transistor. Now, if I take this as my source voltage, now I have something like this. VGS greater than or equal to VTH means VGS is nothing but what? VG minus VS. VG is still at VDD. Now VS is what? VDD minus VTH. This cancel, minus into minus plus becomes, it is VGS is equal to VTH. So now, is this particular expression is true? Then only I can say NMOS is on. Okay, so information is passed only when the transistor is on, and for an NMOS, okay, when drain is at VDD, gate is at VDD, so output will be the VDD minus VTH. Okay, or in other words, if I just take this particular inverter circuit here that we have drawn, okay, so I can get the logic 0, 1 to transition, 1 to 0 transition I'm getting, but 0 to 1 transition there is a threshold voltage drop. Yes, shall we continue? Shall I proceed further? Shall I proceed further? Now, that is where in order to overcome this drop in the output threshold, okay, we will come up with something called the voltage bootstrapping circuit. Okay, this is what is all about our voltage bootstrapping. Okay, how exactly we have to go ahead with voltage bootstrapping, we'll try to see. Okay, so we are ensure we'll come to know what if we do. Okay, then there won't be any voltage drop at the output. So I want finally what, when V in is 0, I want V out to be 1 in this case. Okay, so that's what. So I'll take the same circuit that we had in the. Okay, so just go to the next. So it is voltage bootstrapping circuit. Okay, yeah, okay, this is, so I'll just go with the previous circuit. Okay, this is VDD, this is my still M2, this is my still M1, and this is my V out, and this is the capacitance. Sorry. Now what I'll try to do is I will have one more transistor, NMOS transistor, which I call it as something like M3. This is my M3. Okay, all are NMOS whose output is going as a gate input for this, and this is what I call it as something like Vx. Okay, similar to the previous circuit, the gate of the M2 is still Vx. Now what we'll try to do is we'll have two capacitance. One I call it as C boot, that is bootstrapping capacitance, and another one as something like CS. Okay, some other than C boot I have one CS also. Okay, so this is the capacitor, that CS is capacitor connected from the source of M3 to ground. C boot is from the gate of this and this. Okay, and then the gate of M2 is connected to this VDD. Okay, that means M3 is always on. Okay, something like this. M3 is always on, and M2 is driven by Vx, and we'll try to see what will be the Vx value at this particular point of time. Okay, this is what we have, and this is my V. and this is what my thing. Hope this is fine. This is the voltage bootstrapping circuit. Okay, if I just bifurcate this, okay, left hand side, whatever you are seeing, that is the additional circuitry that I have attached to the previous circuit. Okay, that is the inverter, CMOS. I mean, that's an NMOS inverter basically, because load is also an NMOS. It is not a CMOS now. Now, how this particular circuit works now? Okay, I just write true circuit now. Okay, this is still M2. This is Vx. This is M3. This is VDD. Yes. This is my V in. This is M1. This is my V out. This is CL I take. And this is my C boot. Okay. And then I have another capacitance. Okay. This is my case 1. Okay. For case 1, I let V into B is equal to 1. That is logic 1 or 5 volts. Okay. So M1 is on. This is my Vx. Yes. Now tell me what will be my Vx and what will be my V out. Fast. Yeah. What will be my Vx and what will be my V out? Yeah. Everything is on the screen. M3 is on. M2 is on. Okay. Why M2 is on, we'll try to see now. But assuming that M2 and M3 is on, tell me what is my V out and what is my Vx fast. The gate voltage at M2 and the output voltage. Vx is equal to VDD minus VT. VT3 I'll take it at. Okay, that's good. Okay, what is V out? This is basically VDD minus VT3. Yeah, V out. What is V out fast? Yes. M1 is on. M1 is on. What is my V out? M1 is on. What is my V out? It has to be 0 because I'm getting a least resistance path through my M1. So V out has to be 0. Is that clear? So when Vin is 1, irrespective of the previous circuit and this circuit, the voltage bootstrapping circuit, the moment Vin is equal to 1, M1 is on. Okay, M3 and M2 will be on. Okay, there is a current flowing. And V out becomes 0. And Vx, this Vx, so M3 is on means there is a current flowing. So both CS as well as C boot will charge. Okay. And V out is simply the low output voltage. Okay. So V out will be simply V output voltage, which is nothing but what? 0. VOL is nothing but what? Low output voltage, which is 0 basically. Okay. So through M3, CS and C boot will charge. Okay. And the maximum voltage I'll get at Vx is simply the same thing. This is VDD, this is VDD. Okay, I know that this is acting as a simple pass transistor, so Vx will be VDD minus VT3. That is, the drop is because of the M3 transistor. Okay, so this is what we have. Now, case 2 I'll go. Okay, case 2. This is for case 1. Case 2, the same circuit. What I will change now? What I will change? Yeah, so only thing that I change is the V in from 1, it goes to 0. Okay, so this is V out, this is capacitor. This is 1, this is V in, this is M1, this is M2, this is still M3. This is my Vx, okay. This is my capacitance. This is Cs and this is my C boot. See, one thing you should remember, in case 1 when V in was 1, M1 was on, okay. So V out completely it will discharge its voltage. So that means V out will be at the minimum output voltage, that is 0. And C boot and CS will be charged through this M3 transistor. And I can say Vx is at VDD minus VT3. Okay, this is what I am. Now, second case, I let case 2, I let V into V equal to 0. That is 0, logic 0 or 0 volts. What will happen to my M1? What will happen to my M1?
Off, sir.
It is off. Okay, V in is equal to 0 in this case, V in is equal to 1 in this case. It is off. Now, what really happens now? Yes, what really happens in the circuit? That is very important now. Okay, so now the M3 transistor has already become steady. That means in the previous, because of M3, because of the current flowing, my CS and C boot has charged to the peak level. Okay. Now, what is happening to my VOL now? That is the V out. When this is off, when this completely off, there is no connection between this point to this ground. What will happen to the load capacitance? When M1 is off, that means what will happen to my V out? The moment M1 turns off from on, fast, it is start charging, mean V out from low, it starts increasing. That means you can see that the V out, which was 0 in it previously, it will start increasing. When this is start increasing, there will be a transient current now that will be flowing in this direction. Okay, I'll have current that is flowing through IC boot, and this, all these are steady now. The same thing will go towards my CS now. Oh, this is fine. This is the transient current that goes through the C boot as well as the CS. The moment V out start increasing from 0 to high, I mean start increasing from 0 to towards some VDD or whatever. The maximum has to be VDD now. Okay, so this is what really happens now. Okay, and you can see that voltage across capacitance cannot change instantaneously. Okay, so now this IC and the same current is flowing through the CS. I call it as something like ICS, IC boot and ICS. So what is the current flowing through C boot and CS now? Are they same or are they different now? Fast. Because there is no path here. There is no path from M1 for the whatever the current that is flowing to go. The only path is now through C boot and through CS now, because V out has started getting increasing now. Okay, because VS is fixed now. VS is fixed to VDD minus VT3 kind of thing. Okay, so VS is fixed. Okay, so now the current is in the reverse direction. It is flowing. So in other words, I can say that in the next sheet, I can say that the current through C boot is equal to the current flowing through the CS. Can I or not? Can I or not? Yes or no? Fast. Yeah, so this is what really happens now. Okay, now the IC boot, which was initially charged to Vx, okay, through M3, okay, that is the maximum voltage that it had when the V in was 1, and still now M2 and M1 are still 3 are conducting, but they already become steady. Okay, they have charged this capacitor. Now the V out was increasing, so that's why there was a current that is the opposite that was going to this. Okay, now if I just look into this, what is this ICS and IC boot now? Okay, ICS is nothing but what current that is flowing from Vx to this. So I can simply write ICS as it is the CS capacitance with dVx by dt or dou. Okay, just a minute, I'll just do this. Yeah, ICS is simply CS into dou Vx divided by dou t or delta t, whatever. Similarly, what is my I boot here? The current is flowing from the V out, okay, to Vx. So I can write my IC boot, the current through the boot capacitance. First, it is C boot S. Can anyone tell me? Fast. What is the current with respect to the capacitance that is flowing? I can write it as dou by dou t into V out minus Vx. Okay. Can I write or not? This is the current through the boot capacitance. This is the current through the CS capacitance. Okay. So if this is my C boot, this is my V out, and this is my Vx. This is the current that is coming with respect to the C boot. That is from V out to Vx. So that side is a difference of V out minus Vx by dt into C boot. Whereas for CS, okay, this was Vx, this is CS, this is grounded. This is where my ICS is all about. So ICS is simply what? CS into change in Vx by dt, and that's what I am doing. And since both the currents are same, I'm just equating. So now if I try to integrate both the side, I have VCS into integration of Vx, C boot integration of, or in other words, before I go for integrating, so what I'll try to do is, okay, I'll try to rearrange this now. So CS my plus C boot dou Vx by dou t is equal to dou V out by dou t into C boot. This is what I'm having. Okay, I'm just rearranging the terms in this particular expression. Okay, so I have C boot into Vx by dt. If I take this C boot into Vx by dt towards right side, it becomes plus. It is something like this. Okay. Now we try to integrate this. It is Cs plus C boot integration Vx is equal to C boot into integration of V out. Okay. So when I'm trying to integrate, what is the minimum limit we had started from Vx? It was Vx minus Vt3. This is what? Because this is our reference. Okay. So for case 2, this becomes our reference. So Vx is at Vdd minus Vt3. That is where we have started from. That is the integral part. Vx minus Vt3 till the maximum we don't know. I'll just keep it as Vx. Whereas with respect to V out, we had started from VOL. And what is the maximum V out can reach? If minimum is 0, what is the maximum V out can, if it can go? S fast. What is the maximum the V out can go? Come on. It is a simple inverter, right? Output can be 0 or output can be 1. So maximum integral part, I can take it as something like VDD. Okay, so this is what integration. So the moment if I try to integrate, so this I can write it as Vx minus Vt3 into Vx. Vx is equal to C boot divided by CS plus C boot integration VOL to VDD into V out. So if I try to integrate it, so it is Vx minus of Vx minus Vt3 it is 0 minus Vt3 to Vx is equal to C boot divided by CS plus C boot into VDD minus VOL. Okay. So this is what I am having over here. Okay, so Vx2 minus Vx is equal to VDD. Oh, so this is VDD minus VT3 because this is not Vx minus VT3. This is VDD minus VT3. So this is VDD. So Vx something like this: VDD minus VT3 plus C boot divided by CS plus C boot into VDD minus VOL. Okay. So VOL is basically what? 0. That is what we started. So now you can see that Vx is not only VDD minus VT3, but it is also plus something. It is plus something. Okay. What is this plus something? We'll come back and see. Before that, I'll just go with the pass transistor logic. Okay. I'll just go with the pass transistor logic. Then that explanation becomes easy for me also and for you. So VG is VDD. This is VDD. Okay. This is my drain. This is my source. So what is the source voltage that I'll be having over here? First, what is my source voltage that I'll be having? Okay. When gate is at VDD and drain is at VDD. First,
VDD minus VTN.
VDD minus VTN. Okay. Now, if this is acting as a again, this is again drain, this is source, this is at VDD. Okay. Now, can anyone tell me what should be this now? So gate is at VDD minus VTN. You want VD, okay, you are expecting VDD minus VTN, right? Now, okay. So in order for this transistor to be on, okay, my VGS should be greater than or equal to VTN. You know that. Yes. Now we'll try to calculate what is my VGS, which is basically VG minus VS. What is VG? First, what is the potential at gate now? VDD minus VTN. Okay. Minus of what is the potential that you have just told at source? It is again VDD minus VTN. Okay. What is basically happening now? It becomes 0. This and this cancel. It becomes 0. That means VGS should be greater than or equal to VTN. But VGS I just got 0. So this cannot be off. It cannot be on. It has to be off. So what I will be expecting here? It has to be 0. Yes. Now tell me, it is still on. So what is the maximum voltage the source can have when gate is at VDD minus VTN and drain is still at VDD? It cannot be. No, it is ruled out that VDD minus VTN cannot happen. What can be other thing?
Minus 2 VTN.
Yes,
Sir.
it has to be VDD minus 2 VTN. Okay. The moment when this is the case, when I have VDD minus 2 VTN, then you can see again VGS, VG minus VS, VG is at VDD minus VTN. This is VDD minus 2 VTN. This cancel, this cancel. This is minus into minus plus, so VTN is left. That means VGS in this case it is VTN, which is greater than or at least equal to VTN. This is still not. Is that okay now? And this is what we had said, right? Gate minus of VTS. This is what we are telling now. Now, this is what. Now, suppose somehow if I add plus VTN to gate, somehow I will add to VTN. So what will be my source voltage at now? What is the source voltage now? Suppose if I can add gate, which is VDD minus VTN plus VTN, what will be my source voltage? VDD minus VTN. Okay. What if I add one more VTN to this? VDD, right? What is exactly I'm doing now? drain is at VDD, and I'm ensuring source is also at VDD, provided I'm adding what to get? Some extra voltage, right? I'm adding some extra voltage, ensuring that at the output, I don't want the threshold voltage drop. Yes or no? Yes or no? Yes. And this is what is voltage bootstrapping is basically now. This is voltage bootstrapping basically now. If I just go here, in this case, instead of VDD, if I added VDD plus VTN, my Vout would have been at what potential? Fast. Greater than VDD minus VTN means it will be VDD. Is that clear? Is that clear? So I'm just trying to add that. That's what this voltage bootstrapping is doing. What is this voltage bootstrapping? This C boot, the coupling means this is Vx. Vx is basically what? Vx is basically what? Just a minute. Vx is basically what? Vx is basically VDD minus VT3. Yes. What I exactly want, if this is my VDD minus VT3, I'm sure that this output, if this boot thing was not there, it is VDD minus 2 times the VT3 something. Yes? Yes or no? Yes or no? Yes. So now I have to add some voltage, increase the Vx from VDD minus VT3 to some other extra voltage, ensuring that my Vout, worst case, when the input is low, it should become 1, that is VDD. And that is exactly is what we are trying to do in this case now. Yes, and that's what exactly we are doing in this case. This one now. Hope this is fine. Yes. What is that extra? It is C boot divided by CS plus C boot into VDD. Is that clear now? So what eventually your Vx becomes now? Okay. Now I'll just go ahead with this. Yeah. So I'll just use the same thing. So now I'll just come from the previous Vx. Hope this is okay. Hope you people understood what exactly this is all about. Yes. Yeah. I am just ensuring that whatever the threshold voltage drop at the output was there, I am overcoming that by adding or by increasing the gate voltage. Okay, and that's what we mean by voltage bootstrapping. So increase. So Vx, we got VDD minus VT3 plus C boot divided by CS plus C boot into VDD minus VOL. Okay. So now C boot is very much greater than CS. Means what really happens now? It becomes 2 times VDD minus VT3 minus VOL. Vx, or VOL is 0. I can simply take it as something like this. Yes or no? VOL is basically Vout now. VOL is basically Vout. So when VOL increases, okay, when VOL increases, there will be increase in Vx also. So for example, now, if I take Vx is equal to 2 VDD minus VT3, so that means this basically this capacitance, the CB, whatever we are seeing here, this CB ensures that whenever this VOL, that is Vout, starts increasing from 0 to maximum, this will couple the voltage to this. It will add to the gate voltage, and that's what we mean by the bootstrapping increase. Yes. Finally, we are here. So this is my Vx, which is the gate voltage of M2 transistor. Okay. And now the maximum voltage, output voltage, it can go is something like VDD. If I take, what is my VGS basically now? It is again VG minus VS. VG is at what? Vx, that is VDD minus VT3 minus VS is VDD. So it is still VDD minus VT3. And this VGS, is it greater than VTH or not? Is this greater than or equal to minimum VT3 in order for the M2 to be on? Yes, no. Yes, that is what. This is exactly is what the voltage bootstrapping is all about. Okay. So voltage bootstrapping is a circuit that will try to add to any device, any circuit, okay, whose output is getting dropped by the threshold voltage. Whenever there is a threshold voltage drop, why, you may ask me, sir, why this? Why you want all these things, right? So as I said in the previous past transistor, okay. So I said this, right? If this is driving one more, yes. If this is driving one more, what is eventually happening to my output here? If this is VDD, this is VDD, and this is VDD, and this is VDD, here I get VDD minus VTN, here I get VDD minus 2 VTN, here I get VDD minus 3 VTN, and eventually it may be 0 or anything that is less. Okay, eventually it will be a 0. That means I can't drive anything with respect to the NMOS transistor. So to overcome that, ensure that your gate voltage is increased by some amount so that my output voltage, there won't be any drop. Okay, so 0 to 1 transition is same, and high to low transition is also having the same thing. Okay, so this is what is all about the voltage bootstrapping. Any clarification or doubts at this point? Any doubts, clarification? Fast. Yes, voltage bootstrapping is a method to overcome the threshold voltage drop. That is one of the major aspect of bootstrapping. Okay, and one example I took with respect to the NMOS inverter, wherein when Vin was 0, my output was not at VDD, which eventually it should be, but because of that NMOS, so it is VDD minus VT. Just an example I am taking. You may ask me, so why can't you take a PMOS and do? I can do. Okay, but in some circuitry, if you have an NMOS and but at the output, if you have somewhere the drop, that's why I've taken the NMOS as a load itself. Okay, so in order to ensure that there won't be any threshold drop at the output, we are using this voltage bootstrapping. Voltage bootstrapping is nothing but what? Ensuring the gate voltage, okay, of the load, that is M2, or the basically a driving circuit which drives the output to high, to increase its gate voltage. So from some limited to extra, such that my output remains at VDD, not less than VDD. Is that clear? Yes? Oh, this is fine. Yes, no. Fast. Yeah. So now, so again, all is, we are using a capacitance and all, right? Oh, exactly this capacitance are used. Can we have a active capacitance rather than a passive capacitance? Okay, now we are just in C boot and CS as a passive capacitance. Can we have an active capacitance? See, we replaced a resistor either by using the PMOS, okay, or by using the NMOS connected to VDD, this connected to 0, okay, whatever. Yes, okay, NMOS to VDD, or we can have a depletion NMOS. Depletion in NMOS is nothing but what? Even the gate voltage is 0, this transistor is on. This is an enhancement type of NMOS transistor. When gate is connected to VDD, that is greater than VTN, this is on. Here, for a PMOS, if gate voltage is 0 or above 0, this is on. Okay, so we could replace the passive resistance with the active resistance, that is the load, right? Either by using the PMOS or an NMOS, enhancement or depletion. So can anyone tell me how to replace a capacitance, passive capacitance with the active capacitance? Yes? Anyone? Anyone? It's a simple. It's a simple thing. Anyone? So we had this circuit, right? VDD M2 M1 M3. This is V out. This is VDD itself. This is my VX. And this is my CS. This is C boot. Now, how to replace, just an example, the C boot, that is a capacitor, the passive capacitor with the active capacitor. Anyone? Yes? Fast. If you say yes, tell me. Otherwise, I have to tell you people. That's it. Yeah? No answer from your side. Shall I proceed? How to convert or how to, yeah? This is simply equal to this now, okay? I have M2. So I'll use one more NMOS transistor, okay, which I call it as M4. And below that, I have M1. This is my V out. This is grounded. This is V in. This is Vx. This is VDD. This is M3, whose gate is connected to VDD. This is what? And I'm connecting this. I'm just trying to replace this capacitance with the active capacitance. So now, how to make this M4 to act as a C boot now? What to do? So what I'll try to do is I will try to short these two terminals, source and the drain terminals. I will short. It becomes a single terminal. This is my gate. Now this particular M4 is acting as what now? Fast. Yes. What is this acting as? Come on. I have one gate terminal, and then there is a NMOS transistor. Fast. What is there as a gate? Oxide, right? Yes, I have a gate oxide, and then I have one. So this gate is a metal. Then I have an oxide. Then this is what? Semiconductor, which is basically an highly doped. Again, it is a metal. It is now two terminal now. Gate terminal, source and drain shorted. So now, is this equivalent to a capacitance or not? Yes or no? Yes, that's it. So the moment you make the source and drain shorted, your transistor, NMOS transistor, is simply acting as a capacitor. Okay, so this is how a passive capacitor is replaced with an active capacitor. Hope this is fine. Yes, and this is what was the thing that I wanted to do today. That is the voltage bootstrapping. Okay, so voltage to bootstrapping circuit is used to ensure there won't be a threshold voltage drop at the output. As an example, I had taken NMOS inverter. Okay, when input was 1, V in, V out was 0. Absolutely no problem, because logic low I am getting at the output. When input was 1, sorry, when input was 0, V out I should get VDD, because that is the inversion, but unfortunately I am getting VDD minus VT. There is a threshold voltage drop at the output, because this M2 transistor Vx is at VDD and drain is at VDD. The source of this point cannot go beyond VDD minus VT. Okay, so how to make this to be something like VDD and make sure that your Vx voltage is increased from beyond VDD. It is not that by applying one more VDD from somewhere, no, but just to make sure that Vx is raised above some point. Okay, so in order to do that, we have this kind of structure, wherein when Vin is 1, Vx is driven to VDD minus VT3. Okay, because of M3, that is the gate. And now when Vin becomes 0, this has to go to high, and the moment this is going high, because of this capacitance, it will couple this voltage to this Vx. So instead of Vx, VDD minus VT3, it will be something else also, and that something else is nothing but what this. Okay, and as my V out increases from 0 to maximum, I'm sure, and maximum it can go is VDD. It cannot go beyond that. Okay, because whatever the source is there, the drain has should be there. Okay, nothing like that. So maximum it can go is VDD, but at that particular point of time, my Vx will be simply VDD minus VT3. So there is no change in Vx that is happening. Okay, when VOL is that is V out is at 0, Vx is taken to VDD minus VT3. The moment V out goes to VDD, my Vx again remains to VDD minus VT3. Okay, so this is how this capacitor CB, okay, couples the output voltage to Vx in order to maintain V out to be maximum, that is VDD. There won't be any drop. Okay, and finally, how to realize a active capacitor rather than the passive capacitor. This is how. Okay, short the source and drain of the MOS transistor. Okay, so you will just simply consider that as something like an active capacitor. Yeah, so this is what the thing that I was supposed to do. Yeah, hope this voltage bootstrapping, why, for what, and how we can implement this voltage bootstrapping and all. Hope this is fine. Yes. Any clarification? I'm happy to take. Otherwise, I think you can